right, guys, let's start talking about the bell work here. So my first question is on the first statement here where it says a third degree polynomial function. Tell me what types of things I would want to look for on the graph if it is third degree. What'd you say? What kinds of things would I be looking for? If it touches the x-axis, what's the most number of times that it could touch in order to be a third degree? 3. So third degree polynomial, I know it has a maximum of 3x intercepts. Does that mean it has to have 3x intercepts? No, but it can't have more. What else should I also be watching out for if it's degree 3? Is 3 an even or an odd number? Odd. So what should I be looking for on the graph if it is an odd degree? Opposite ends. Are there any of the graphs up here that meet these criteria? No more than 3x intercepts and opposite ends.
Yes, C.
C.
And A.
A could be because it has no more than 3x intercepts and it has opposite ends. However, when I look at 3, that looks like what? That looks like a linear function. What's the degree on a linear function? 1. A linear function is degree 1. For everything other than a linear function, you're almost always going to see some kind of wiggle in there somewhere. It's different sizes of wiggles, but linear functions are the only ones that are perfectly straight. So I like what you said. That's absolutely what you should be looking for. If you said C or A on a test and you said, well, it has no more than 3x intercepts and the ends are opposite, I would give you credit for that because you justified your reasoning using what we've learned. What about number 2? Which of these graphs are showing me a negative leading coefficient? B and C. What are we looking for on the graph for a negative leading coefficient? Right side is going down. And B and C meet those criteria. All right. Number 3, domain and range, all real numbers. How do I know by looking at the graph if the domain is all real numbers? How do I know by looking at the graph if the domain is all real numbers? Yes, domain is talking to me about my x's. My x-axis goes left and right, so I'm looking for arrows that point both left and right, more or less. It doesn't have to be all the way left and all the way right. They can be tipped, but I have to have an arrow on the left end and I have to have an arrow on the right end. Does graph A have an arrow on the left and the right? Yes. What about graph B? Yes. Yes. On the left end of the graph, it has an arrow. On the right end of the graph, it has an arrow. What about graph C? Yes. Graph D? Yes. All of these graphs show a domain of all real numbers. How do I know if the range is all real numbers? Yeah. Domain, I'd be looking this way. Range, I'm looking this way, up and down. It has to be able to get all the negative outputs, and it has to be able to get all the positive outputs. So you have to have one end that points down and one end that points up. Does it matter which end is doing what? As long as one points down and one points up. Does graph A have an end that points down and an end that points up? Yes, so it can get any kind of negative output. It can get any kind of positive output. So graph A meets this criteria. What about graph B? Does graph B have a range of all real numbers? Why not? They're both pointing down, so I can get any kind of negative output, but I can't get any positive outputs at all because there's no part of this graph that's up there. So far, so good? What about graph C? Does it have a range of all real numbers? Yes. How do we know again? Yep. One end is pointing down so I can get any kind of negative output. One end is pointing up so I can get any kind of positive output. What about graph D? Does that one have a range of all real numbers? No. Why not? They're both going up. There are negative outputs that I'm not going to be able to get. So far, so good? All right. Number 4. The end behavior as x arrow infinity, f of x arrow infinity. Can somebody read this back to me in plain English and tell me what I'm supposed to be looking for? Yes, ma'am. The right side is going up. So which of the graphs show the right side going up? A and D. What about this last question? It says no real zeros. Where would I look on the graph for that? X-intercepts. Real zeros are the same things as x-intercepts. Which of these show no real zeros, no x-intercepts? B. Graph B is the only one that shows no x-intercepts. So far, so good? All right. So we're just coming off of a week where we spent almost the whole week on one section of the book, which meant one homework assignment. When is that homework due? Today. We did 2 of those problems in class yesterday. All the others I chunked out day by day. Today is a 1-day lesson. It's short and sweet. Homework assignment for this one is due on Monday. Doesn't have very many problems either. You're not going to need your calculator for what we're doing today. But we're going to talk about what we've done with the calculator over the last couple days because it relates to the 2 big ideas we're talking about today. In your books, page 223 for me. Page 223. The first big idea that we're going to talk about is called the location principle. The location principle tells me if I'm trying to graph a function, so I'm making a table of values, so I've got my list of x's that I'm plugging in and I'm putting it into my calculator like we've done over the last couple of days. If I put a number in and I get my output back out, I hit enter and I see the number that I get back as a result, and it's a negative number. And then I move to the next number on my table, just the next number that comes on the number line. And I plug that one in to the function. I put it into my calculator and I hit enter. And I get a positive output. That first point, the one that had the negative output, would be somewhere down here, right? Because it's got a negative y. The other number that has a positive output would be up here somewhere. Somewhere in between those, it had to cross the x-axis. I might not see it on my table because it wasn't one of the whole numbers that I plugged in, but I know it's got to cross the x-axis in between there somewhere. That is the location principle. So here I've put up in words exactly what I just said to you guys. If I substitute a number into the function and I get a negative output, and then I substitute the next bigger number in and I get a positive output, then somewhere in between these 2 numbers, there would be an output of 0. It's going to be some kind of decimal. I don't know what it is, but I know it's between these 2. Does that make sense? Yep. All right, let's look at an example to practice this. If you look just a little bit down the page, we're still on 223. We're going to practice this here. We're also going to put it together with what we know and what we've been talking about all week about polynomial functions. What's the degree of the polynomial that they gave me here? Degree of 4. So tell me things that I know because the degree is 4. It's even. The ends are going the same way. It is positive. Where do I look for that? Do I look at the 4 for that? I look in front of the x to the 4th. Right here, my leading coefficient is 1, which is positive. So what does that tell me? Both sides are going to go up. This part tells me that the right side goes up. The fact that it's even tells me that the left side is going to play follow the leader and it's going to go up also, right? So the left side and the right side are going up here. Yes, ma'am?
So the 4 tells you about the right side?
The 4 tells me that my ends are going the same way. From the 4, I don't know if they're going both up or both down. I just know they're doing the same thing. The leading coefficient being positive tells me only what the right side is doing. Since it's a positive number, it's going up. Because the ends are the same, the left has to also go up. Does that make sense? Okay. How many possible real zeros could we have? 4 real zeros. Why? Because it is a 4th degree polynomial. So there is a maximum of 4 real zeros. Look at this table. Which of these rows is the input? Which one would I be substituting in when I'm putting stuff in my calculator? Top one. Here's my input. Give me just a second, guys. How did I know by looking at this table that the top was the input? What was it about the table that told me that the top was the input? Because it says x. Whichever part of my table is giving me my x's is always going to give me my inputs. So this bottom row must be telling me what? The outputs. That's my f of x's or my y's. I want you to look at these outputs. We're going to use our location principle. What type of number did we get for the first output, a positive or a negative? Positive output. When I did the next number, we got what kind of output? Positive. What about when I put the next number in? Positive again. What about when I put the next number in? Negative. I had a positive output here and a negative output here. When I put 0 in, I got a positive output. When I put 1 in, I got a negative output. So what had to happen between these two x's? It's that location principle. What had to happen if it went from being a positive number to being a negative number? It went down and it crossed what?
The x-axis.
It had to cross the x-axis. So somewhere between 0 and 1, there's an x-intercept. Circle these two right here. Somewhere between these two, there's an x-intercept. So far, so good? All right, let's keep looking at this table. I'm going to pick up right where I left off. I had a negative output right here, right? Put the next number in my table and I get what kind of output? Negative. Put the next number in and I get a positive. Did my outputs just change signs? It started off a negative somewhere down here. And for the next one, I got a positive somewhere up here. So what had to happen between those two? Has to cross the x-axis. Somewhere in between 2 and 3. There's an x-intercept. All right, and they wrote that down for us right here. Somewhere between 0 and 1, and somewhere between 2 and 3, there are x-intercepts. We are going to sketch this graph. Am I going to be able to fit all of the points from this table on that tiny little graph they gave me? Nope. This is why we have to use the other information that we have to get a reasonable sketch drawn. Can I put this first point on, -2, 29? Can I put that on this graph? What about the next point, -1, 3? Will that one fit? Let's plot it. -1, 3. It's going to be right here on my graph. Plot that point for me, thank you. Sorry, sir. All right. Tell me one more time, why couldn't I fit this one on the graph? It's too big. This one fits on my graph. Will the next one fit? Yes. 0, 1. Let's plot that point. Will the next point fit? Yeah. 1, -1. Let's plot that point. What about the next one? Will this one fit? I can fit 2, -3 on there. Let's plot that one right down here. Can I fit the next point, 3, 19 on there? Why not? 19 is not on the graph because it's too big or too small? Too big. What about 4 and 113? Will that fit on my graph? No. No, because it is? Definitely too big. If you didn't know any better, what shape would you think that was? It looks like a line. Is this going to be a line? Mine doesn't look like a straight. I made my dots real big too. Is this a line? It looks like it from what I got plotted, but I want to know from what you know about polynomials. No. Tell me about the ends. What did you tell me the ends were doing?
Going the same way.
They're going the same way. Are they both going up or both going down? Up. Why? Leading coefficient is positive. If I look at my table, I see this end is up high. I see this end is up high. So I'm going to trace through these points, but I know it's going to have to come and curve up over here. So it comes down through these points. I'm going to give it a little wiggle here. My ends are going the same way. It's very high over here. It's very high over here. Where did we say it was going to have to cross the x-axis at? In between 0 and 1 on the x-axis. So I see it crossing the x-axis in between 0 and 1. It's also going to have to cross the x-axis where? In between 2 and 3. So I know it had to go up really fast because it had to get up above the x-axis before I got all the way over here. Does that make sense? Is this a precise sketch? No. Does it have all the most important features that we've learned about so far? That's what I expect to see on sketches. Did you use your table? Did you plot the points that you could? Did you make the ends do what you knew they were supposed to do based on your leading coefficient and your degree? That's our first big idea today, the location principle, being able to look at a table, and if I can't see zeros on my output, I can find what it's in between. Second big idea for today. Go ahead and turn the page, 224. Second big idea today is about extrema. We've already talked about extrema. Do you guys remember back in August when we talked about extrema? Do you guys see anywhere on this graph that you would describe as a relative minimum? Yeah. Relative minimum would be like the bottom of a little valley, right? What point would be a relative minimum here? Point A. There's a relative minimum.
Oh, my bad. I ain't
Is there a point on here that would be a relative maximum, like a little hilltop? Point B. When I want to talk about all the valleys and all the hilltops, and I don't want to say relative minimum, relative maximum, relative over and over, we can call them extrema. These are the extrema of my graph. I can tell approximately how many extrema, how many hills and valleys my graph is going to have by taking the degree of my polynomial and minusing 1 from it. So, for example, a degree 3 polynomial has a maximum of 2 extrema, because I took the degree and I minused 1. So I want you to practice with these. If I have a degree 7 polynomial, what is the most number of hills and valleys it could have? 6. What about if I had a degree 20 polynomial? What is the maximum number at extrema, hills and valleys, that this graph could have? 19. Whatever the degree is, you minus 1 from it. That is the most number of turns you could see on the graph. Does that make sense? All right, we've got 2 more examples that we're going to knock out together. Look just a little further down the page at example number 2. Look at the function rule. F of x equals this piece right here. What is that degree? Degree is 3.
My bad. I tweak.
There we go. Degree is 3.
I can't see.
What is the maximum number of extrema? That's another reason I had you in the front, sir.
Huh?
I said that's another reason I had you up in the front, sir. Being able to see the board is kind of one of the most important parts of sitting in class. That and listening. What is the maximum number of extrema that this could have? 2. Max number of extrema. How did you know it was 2?
Oh, you subtract about 1.
Yep, take my degree and minus 1 from it. Look at this graph with me. Do you see any extrema? Extrema are relative maximums, relative minimums, hills and valleys.
She just said that.
You don't have any room to speak, sir.
You got the wrong people sitting in front.
How many extrema do you see on the graph? 2.
Yeah.
Could there have been any more?
Yes.
Where?
Could there have been any more?
Oh, not on this graph.
Not on this graph. Why not?
Because it's only 2. Like, what you mean? Why not? Why? Let's say if it was like
Back to here. What is the maximum number of extrema it can have?
Oh, 2. Oh.
If it's a degree 3, the most it can have is 1 minus this. So coming back here, I see 2 extrema. Could it have had any more?
No.
Why not?
Because only if it's a degree 3 or less.
If it's a degree 3, it can have 2 or less, but it can't have more than that. Is this one a relative maximum or a relative minimum?
Relative maximum.
Relative maximum. If I asked you where on the x-axis that relative maximum is happening, like the x part of the ordered pair up at the very top, you'd tell me it's about what? If I wanted to know where on the x-axis or the x part of this ordered pair it's hitting its peak. I don't want the y part. I want the x part of that ordered pair. -2. Yeah. It looks like it's just a little bit to the right of -2. So -2, -1.5, somewhere in there. So it is near x equals -2 or x equals -1.5. I'm just asking you to ballpark it for me. What would the x part of this ordered pair be?
Probably like 4.
X part.
Oh, the x.
The x part.
Like 3.
No, you guys already answered this one for me.
Oh.
Is this a relative maximum?
Yeah, it's gonna be
No, it's a relative minimum.
It's a relative minimum. That is absolutely enough. You'll be right back up here in like 2 seconds.
Miss Bo.
Honey, you're the one that's loud. That's the thing I have a problem with, and that's the thing we keep talking about.
Wait, what I do?
She just told you what you did. You loud.
Let's stop talking. Let's stop talking. Let's stop talking. Just back up here.
Someone at the door.
Thank you.
I think.
Oh, wait, they might be the other class.
Yeah. All right. Relative minimum. I know relative minimum means a low point. I want to know about where on the x-axis this is happening. So the x part of this low point would be about what?
1.
About 1. When I look at the table, does that match what I see on the graph? Is this the lowest thing on the table?
Wait.
Over in this area. Because remember, relative means I'm staying local to right here. Is this the lowest y in this general vicinity? Yeah. What's the highest y back here? 4. That's right about where we said that maximum was. One more example with me. We're going to look at example number 3. It's on the next page. Got to stay with me, sir. You just missed that whole example, honey. Head up. First thing I want to talk about here on this example is domain and range. How do I find domain from the graph again? Left and right. So I want to look from left to right. Your book is using this notation right here to talk about the domain. We're going to talk about how to write it our way and how to write it their way. How do I know if it's all real numbers? What would I see on the graph? Domain means I'm looking left and right. What would I want to see on both ends if it's all real numbers? What would I be looking for if it's all real numbers? It's not up and down. That'd be my range, but I like what you're thinking. For domain, I'm not looking up and down. I'm looking left and right. I want to see, are there arrows on both the left and the right end? Does this one show me arrows on both the left and the right end? No. It only shows me an arrow on which end? Just the right end. Why is there not an arrow on the left? Because it starts at 0, and what are we talking about here? Years. I don't have any information before year 0, so I can't talk about it.
It's not real. Well, no, it's real. It's just...
I mean, in this case, they're talking about years before 1930. We know that there were years that came before then, but I don't have any information for it. So what's the smallest number of years that we can talk about? Year 0.
So technically like 1930.
1930, yep. I like that you said that. We're going to write that in. This goes with the year 1930. But on my graph, it's 0, so I'm going to leave it as 0. All the other x values are bigger or smaller than that? Bigger. So how do I write that in my interval notation? Infinity. All the x's are greater than or equal to 0. What about the range? Where am I looking now for range? Up and down. I start with down, and then I move my eyes up from there. What's the lowest I can ever go on this graph? Look at the table, make sure, because that graph, they've done some estimating.
Is that an arrow or a dot?
Right here? I'm saying I start by looking down. I go as far down as I can, and I write that first when I'm talking about the range.
I know I was talking about where they're at, where it's set to 0 right there. Is that an arrow or a dot?
Oh, sorry, I misunderstood your question. Right here, that's a dot.
Oh, so the farthest you go down is 0.
Are you sure?
So that's a dot. It's
7.708. Why is that the lowest? Where did she get that kind of a decimal number from? Yes, sir.
Is it because that's where the last, like, right before that 0, is that was the last point right there?
What do you mean that was the last point before the 0?
Never mind. Wait, hold up.
Oh, because the table right there on the 0.
It's not hitting exactly on 0. It's just a little bit above, but it's really hard to tell from the graph.
That's what I mean.
How did she know it was 7.7? How could she be that precise?
It's right there.
It's on our table right here. What do we call this? Y-intercept. Does this graph ever go lower than that y-intercept? No. So my range starts at 7.708. What's the highest it ever goes? Infinity. How do I know? Because there's an arrow. So all of my outputs, all of my y's are bigger than or equal to that y-intercept. That's the lowest this particular graph ever goes. So far, so good? We have just a few more questions to answer about this graph in this table. The questions are on the next page, though. I'll make sure I've got the graph up on the screen so you guys don't have to flip back and forth. Does it have any relative maximums or relative minimums? Does it have any extrema? Does it show a relative max, a relative min, or both? Both. Tell me where the relative maximum is. So right up here, what x values is that in between? 50 and 60. But this is 50 and 60 years since 1930. So 1930 plus 50 would be what? 1980. And 1930 plus 60 would be 1990. So there is a relative maximum between 1980 and 1990? You told me there's relative minimum on here too. Give me the x values that it's in between so I know where to look. In between 80 and 90. Somewhere in between here is my relative minimum. So what years would that be between? It's between 80 and 90. So to find the year, I do 1930 plus 80. What is 1930 plus 80?
Oh, that's easy.
2010.
See, I was gonna say that, but they stole my name.
What is 1930 plus 90?
220.
2020. So in between 2010 and 2020, there's a relative minimum. Talk to me about the end behavior. Your book has this printed statement in it that we have to finish. Which end are they asking us about here? The right. What is the right end doing? Going up. How do I say that? How do I finish the sentence? Positive infinity. Your book doesn't have this in there. Why not? Doesn't have a left end. Why not? What did we say about this side over here?
Stop.
It stops. It does not have an arrow. So I don't talk about the left end. No left end behavior because no arrow on the left side. In the relevant domain, the y-intercept is at, where did we say our y-intercept was again? 7.708. Is there an x-intercept on this graph? No. It's hard to tell just by looking at the graph, but I know my y-intercept shows me that we're up a little bit off the x-axis. Does it ever dip down and touch the x-axis? Nope. Does this graph show any kind of symmetry?
No.
No. Can I take it and fold it in half along a vertical line and make it match up? Can I take it and give it a half a circle twist and make it match up? Nope. This graph does not have symmetry. That is what we needed to get through for today. There were two big concepts. What were those two big concepts again? What were those two big ideas that we covered? What was our first example about? Extrema. That's what example 2 and 3 were about. What are extrema again? Maximums and minimums. What was our other big idea? First example.
Oh.
You're right, it does have to do with my intercepts.
It was when we had that table.
The degree thing?
It's not our degree, it's my location principle. If I'm plugging numbers into my calculator and into my function, I get an output that's positive, and then I plug in the next number and I get an output that's negative. What happened between those two x's? It crossed the x-axis. What about if I'm plugging numbers in and I get negative outputs, and then I plug the next number in and I get a positive output? It had to cross the x-axis. That's my location principle. That's our two big ideas for today. Homework that's due Monday, it's these 6 problems. If you want to work on them in your book, you will turn them in on McGraw-Hill, just like we've always been doing. 6 problems is what's due for Monday. All right? Sounds like a plan. I hope you guys have a fantastic weekend.